Hey everyone, welcome back. We have just so much stuff to do, let's get jumped into this right away. So, we can talk about parallelograms. So today we're actually going to cover three shapes. They're all special kinds of parallelograms, shapes that you should already kind of be familiar with, but we're going to go over some properties that maybe you are less familiar with. So these three shapes are, first off, a parallelogram that has four congruent sides. So this is a rhombus. Okay, so I'll just make some notes for what these things are. So a rhombus, our one note here is that it has four congruent sides. Okay. We have a parallelogram that is all 90-degree angles. So this is a rectangle. All right, and so this has four right angles. All right, and of course we have squares, which has both of these properties. So this has four congruent sides, and it has four right angles. All right, so none of this is really difficult on its own. Obviously, you've known probably what these shapes are, probably since like elementary school, perhaps. Maybe not rhombus, but you've been familiar with these shapes. You're saying, well, what's going on here? So the difficulty, like a lot of things, comes from the nuance, the kind of overlap of properties. Okay, so we're going to go over specific properties for rhombuses and rectangles. These are in addition to the properties that these all have because they are already parallelograms. And then you have the added layer that when you have squares, a square, because it has both the properties of rectangles and rhombuses, shares these properties as well as all the properties of parallelograms. So it's really keeping track of the layers that exist here, okay? And so this little Venn diagram might be able to help us real quick. So this is, we'll take the larger universe here and call this parallelograms in general. Okay, so parallelograms just have opposite sides parallel. All right, and so our couple different special parallelograms here, we have rhombus. Okay, so rhombus has four congruent sides. And we have rectangles, which have four right angles. Okay, so for a rhombus, we draw kind of an example here. So I know this is going to be a rhombus because I will mark that I have four congruent sides. I have a rectangle here. This has four right angles. Okay. So what would exist on the outside would be one that is neither of these. So one that doesn't have right angles and it does not have four congruent sides. So it would be just something kind of like this. We can still mark the parallel sides. Okay. So in this Venn diagram now, the overlap, something that will have these four right angles as well as these four congruent sides, this is where we're going to put squares. So you can kind of see the hierarchy. So now, after we do all these things, so you'll notice in the notes that we do today, I'm actually not going to outline any properties of squares. Squares don't have any properties unique to themselves, but what you're going to see is that if you have a square, it is going to have all of the properties of a rhombus, it is going to have all of the properties of a rectangle, it is going to have all the properties of parallelograms, okay? And then if you go one step higher, it has all the properties of just quadrilaterals in general, mainly that, you know, the sum of the interior angles is 360 degrees, stuff like that. Okay. So first example here, for any rhombus, QRST, decide whether the statement is always or sometimes, or I suppose never or never true. That's usually the three choices we have. A little spoiler that it's probably never then. So something that can be true here, first off, I'm going to kind of draw a rhombus. So something you want to do when you're determining these is even though, yes, a square is a rhombus, if you're given a question that specifically says rhombus, okay, don't draw a special rhombus. So if it says that you have a rhombus, draw the most generic rhombus you can. Okay, so yes, I know squares are also rhombuses, but if you just draw this with 90-degree angles, okay, you might accidentally say something that you're not actually allowed to say. So I'm going to draw the most obscure, or the most ambiguous rhombus that I can. So Q being congruent to S. Is Q going to be congruent to S? Well, all I know on a rhombus is that the four sides are congruent, but this is always true. Okay, and even though none of our definitions here for rhombus said anything about angles, think for a second as to why this must be true. Because a rhombus is still a subset of parallelograms, and we know that the opposite angles in a parallelogram are congruent. Okay, so a rhombus is a parallelogram. All right, and the opposite angles in a parallelogram are congruent. Okay, so this is a case where we have to actually apply parallelogram properties to answer this question about a rhombus. All right, here I'll use the same picture here for Q being congruent to R. Is this always, sometimes, or never true? This is not never true. Okay, this is actually going to be sometimes true. All right, so in the case of a rhombus, it will sometimes be the case that the adjacent angles will be congruent. Okay, so we can say something like the adjacent angles of a rhombus will be congruent if it is also a square. Okay, so if this rhombus happened to be this more special rhombus, it would be the case that the adjacent angles would be congruent. So that is a sometimes. All right. Moving on here, we're going to classify the special quadrilateral and explain your reasoning. Okay. So what we have here, first thing I see is that we have the four congruent angles. Okay. So that tells me that it's a rhombus. And you just want to keep looking at the properties to see how specific can we go. So if it were more specific than a rhombus, it would be a square. A square would have to have the 90-degree angles of a rectangle, which this one does not. So the furthest I can go is to say that this is a rhombus. Okay? So my explanation should be something like all four sides are congruent, but it does not have the four congruent angles to make it a square. Something like that. So you want to have just a little note as to why it is a rhombus, and almost an additional note as to why you cannot go further and call it a square. Okay? So the practice questions here again, for a refresher, this is a good spot for you to just pause the video, try these on your own, and then come back and see the answers. Okay? So for any rectangle EFGH, is it always or sometimes true that FG is congruent to GH? So similar to the question we just did. So first thing I'm going to draw the most generic rectangle EFGH that I can. Okay, and so FG is kind of the top part that I have here. GH is the part on the side. These being rectangles, we know that the opposite sides are congruent. We don't know that the adjacent sides are congruent. So this is very similar to the last question we did. This is going to be a sometimes question. Sometimes, okay. This will only be true if EFGH is also a square. So if it were a square, it would also have the rhombus properties, where all four sides would be congruent. All right, a quadrilateral has four congruent sides and four congruent angles. Sketch the quadrilateral and classify it. So if I have the four congruent sides, we know that it is at least a rhombus. Okay, And if I have the 4 congruent angles, right? If I just show that I have 4 congruent angles like so, and if you don't know what these angles are, I have 4 of them, and the sum of the interior angles is 360 degrees for a quadrilateral. So this tells you that the 4 congruent angles have to be 90 degrees, which means that this actually has to have 4 right angles and 4 pairs of congruent sides. That makes this a square. Okay, so that's all the pretty basic stuff. This starts to get challenging right about here, because the properties of the diagonals is always, these are always the properties that trip people up a little bit, okay? So what do we already know? We know that the diagonals of a parallelogram bisect each other, okay? These have additional properties that are only true in specific cases, all right? So these first two are for rhombuses. So this is a way to classify something as a rhombus without using the definition being that it has 4 pairs of congruent sides. You can actually determine if it is a rhombus by using one of these properties here. So a parallelogram is a rhombus okay, if and only if, bring this guy back. So if and only if, remember, that means that this is a biconditional statement. Okay, so a parallelogram is a rhombus if and only if the diagonals are perpendicular. Okay, so remember this if and only if. I'm going to shorthand it on the other ones. That's the if with 2 F's. So this means that this can be proven in 2 different ways. So you can prove that the parallelogram is a rhombus if it has perpendicular diagonals, okay? And you can also prove that if you have a parallelogram with perpendicular diagonals, that it is a rhombus, okay? So this is both a property of a rhombus and a way to prove that a parallelogram is a rhombus, okay? Another property here to determine if it is a rhombus. So a parallelogram is a rhombus, again, if and only if the diagonals bisect the opposite angles. Okay, so remember now, because we're still talking about parallelograms, we know the opposite angles are congruent, and now we're saying if we know those opposite angles, like here, the big angle C and the big angle C are congruent, if this were also a rhombus, then the diagonals would cut those congruent angles in half, which means you would actually have now 4 tiny congruent angles. Okay, on that side, same thing going the other direction. You would have 4 different congruent angles going that way. Okay, and now our last property here is for a rectangle. So a parallelogram is a rectangle. Again, if and only if the diagonals are congruent. Okay, so because it's a parallelogram, we already know that the diagonals bisect each other. Now, if in addition to them bisecting each other, they are actually congruent, that would mean that you have 4 congruent halves. That will make this a rectangle. So these two, I like to kind of try to separate these a little bit. These top two, again, these are properties for a rhombus. Okay, and just this bottom one here is an additional property. Oh, we're off the screen there, for a rectangle. Okay. So the difficulty here is keeping track of these, but also if you notice we didn't say any of the squares, right? That's because a square would get all of these. Because a square is both a rectangle and a rhombus. So if you were to start keeping track, you see squares have lots and lots and lots of properties. Okay? All right, so let's try to use these diagonal properties now to answer a couple of questions. All right, here we go. So we have a kind of carpenter here, kind of framing a window. You clearly want the window to be a rectangle. If you can't see, this is in red, so it's not showing up very well for you. These top sides are 33 inches. The bottom side is 33 inches. The sides are both 44 inches. Okay. So given that we have those measurements, can we assume that it's a rectangle? It sure looks like a rectangle. However, just knowing these things, we cannot prove that it is a rectangle. Okay. So the two pairs of opposite sides being congruent. So the two pairs of congruent opposite sides is sufficient only to prove it is a parallelogram. Okay, so you might think, well, to prove it to be a rectangle, you need this to be 90 degrees. Okay, but in construction, people you don't really use protractors so much in construction. Now, yes, they do have things that literally just are right angles because you just plug that square into the corner to see if it's a right angle or not. But you using a protractor is not really something that you would do. So actually what they do is they use the diagonals. Okay, so if you were a carpenter, you'd be aware of this rectangle property that the diagonals are congruent. So obviously if you were cutting the wood to be 44 inches, 44 inches, 33 inches, 33 inches, those have to be congruent. Okay, so you don't really have to go back and measure those after you've done the cutting. But something that you do is you measure the diagonals, and you know that the diagonals of a rectangle are congruent. So that's one way to do it without trying to measure the angles. So here we measure the diagonals. The diagonals come out to be a little under 55, so 54.8 inches and 55.3 inches. What can you conclude? Well, we conclude that we're in a small bit of trouble. Okay, so we can conclude that it is not a rectangle. Okay, because rectangles have congruent diagonals. All right, so that means that this is indeed a parallelogram. Okay, so it's not going to be a perfect rectangle, unfortunately. All right, so we have a little bit of the proof of 811. All right. So that's the proof. I didn't number them. This is the idea that if you have a parallelogram, it is going to be a rhombus if and only if the diagonals are perpendicular. Okay, this is only half of the proof because the if and only if is a biconditional, so it actually works both ways. This is a proof of this in one direction, like the band, and then you'll have to go back and prove it the other way, which is just going the opposite direction. It's not too different, so I'm not going to prove it both ways. I'm just going to prove one direction of this. So again, we're going to set up our statements and reasons here. All right. So our statements, first thing you always start with are your given. So I'm going to say A, B, C, D is a parallelogram. And the second thing is that AC is perpendicular to BD. Okay, so these are our givens. All right. So what do we know? So we want to think, what other things do we know? Because it's a parallelogram, I see that we have these parallel sides. That's already marked. Ends up being a little bit of a red herring because I actually don't really need to use that. What I'm going to use, I'm going to use some diagonal properties from a parallelogram. So we also know that in a parallelogram, the diagonals bisect each other. So that means in this case that AX is going to be congruent to CX. And it also means that DX is going to be congruent to BX. Okay? And this is because in a parallelogram, the diagonals bisect each other. Okay, so we get this point X is the midpoint of each of those diagonals. And now that we have these perpendicular segments here, okay, we actually can see that all of these angles here are 90 degrees. So this is a property of perpendicular lines. Okay? So the measure of angle AXB is the same thing as the measure of angle BXC. Oops, this should be equal, not congruent, which is equal to the measure of angle CXD, which is equal to the measure of angle DXA, which is 90 degrees. This is a property, or the definition of perpendicular. Really, the idea is the perpendicular leads to right angles. The right angles, by definition, are 90 degrees. I'll try to get away by just calling this a property of perpendicular lines. Okay? But you can follow that train of thought there. Okay? The perpendicular lines leads to the four right angles. The four right angles are all 90 degrees. Okay? So now what we have is we have all these tick marks here. We have all these right angles here, which means we actually have a bunch of congruent triangles. So I'm going to be careful with the naming. I'm going to call this ABX triangles congruent to CBX is congruent to triangle CDX, which is congruent to triangle ABAD. And these are all congruent by side, angle, side. So they all have a one tick mark side, then a right angle, then a two tick mark side. Okay, so we have actually four of these. And now that I have these four congruent triangles, right, think about what we're trying to do. I'm trying to prove that it's a rhombus, which means I need all of these outside sides to be the same. And that is now what I have. So AB is congruent to CB, is congruent to DC, is congruent to DA, and these are all congruent by CPCTC. Okay? And if we had finals this year, this would be on your final. What does CPCTC stand for? The corresponding parts of congruent triangles are congruent. Okay? However, that's not the end of our proof, because we actually need to prove that it is a rhombus. I've just shown that these four sides on the outside are all congruent. That is pretty much all I need, though. So ABCD is a rhombus, and this is just the definition of a rhombus. Okay, we have shown that it has four congruent sides. Okay, super. All right. So again, this is only half the proof. If I were to do a full proof of this theorem, you would have to start with the parallelogram, start with it being a rhombus, and then because it was a rhombus, you'd have to go backwards and prove that it had perpendicular diagonals. Okay, so you can try that. It's not too much harder a proof than the one we just did. All right, so these are all our properties. We're going to just close today with a couple extra practice questions here, a couple extra proofs. Okay, they're not too bad. The diagrams look a little odd. Here I'm going to really kind of space this out. I think this takes up a fair bit of space. So, write small. So again, we're always starting with our givens. So we have triangle GEC is congruent to triangle GHX. And we also have that GEBH is a parallelogram. Okay. And we're trying to prove that GEBH, so the same shape, is a rhombus. So let's first see what we're looking at here. So we have GEBH. So this thing in the middle, okay, if it looks kind of squarish, we know that it's a parallelogram and prove that it's a rhombus. Okay, so you want to think, well, how much more do we need to know about a parallelogram to know that it's a rhombus, right? To show that it's a rhombus, we either need to prove that the diagonals are going to be perpendicular, or we need to prove that the sides are congruent, okay? Now here we have GEC, which is this triangle up here, and GHX, which is this triangle down here. If I could prove that this angle GXH was 90 degrees, that would be good. But all I know is that this angle is the same as this angle, So that doesn't tell me that it's 90 degrees, though. I just know that they are congruent. Okay, so that seems like it's out. So what I need to be able to prove is that the all four sides are going to be congruent to each other. So what I do know, though, already is that because it is a parallelogram, okay, I do know that the opposite sides are already going to be congruent. That's a property of our parallelogram. So I know that GE is congruent to HB, and I know that GH is congruent to EB. Okay, so this is just a property of parallelograms. Right, mainly the opposite sides are congruent. Okay, so I know that I have this pair that are congruent, this pair are congruent, but I need those pairs to be congruent to each other. And that's what I can use here, because these are my congruent triangles. So GE and GH are corresponding sides, like that. So I can say that GE is also perpendicular, or congruent to GH by CPCTC. Okay? And now this lets me now chain all of this stuff together. So because I know that these two things are congruent, and I already know that GE is congruent to the opposite side, GH is congruent to the opposite side. So those are my four congruent sides. Okay? So GE is congruent to EB, is congruent to HB, is congruent to GH. And this is all by the transitive property of congruence. Okay? So just linking these number 2 and number 3 together, you can get that you have all four of these are congruent. And that makes this a rhombus. Is a rhombus. And this is by definition of a rhombus. All right. So jumping quickly in this last one here, right? Lots of proof examples in this. So that's why this video is actually pretty long. I'm sorry. So again, we're going to start with our givens. Jane is a parallelogram. And JXPE is a parallelogram. And XP is perpendicular to EN. And it's all given. All right. So I'd highly recommend pausing this and trying this yourself. It is not nearly as hard as it looks. It looks like there's a lot of weird stuff going on here. Okay. So first off, if I want to prove this is a rectangle, you got to think about what does that mean my proof needs to get to. I need to get to there being four right angles, four 90-degree angles. Okay. I have this pair of perpendicular lines. That will let me get to a couple of right angles, and then I just need to kind of extrapolate on that. So here's all the stuff that I know. So I have two parallelograms here. I have this little one on the left, and I have this big thing. The whole thing is a parallelogram, and it is that whole thing that I'm trying to prove is a rectangle. But knowing already that it's a parallelogram, we know that J is congruent to angle EPX. We know that JEP is congruent to PXJ. So these are just the opposite angles in that parallelogram. Okay? And also in the large parallelogram, angle J is opposite angle N. And angle JEN is congruent to angle A. So we have, again, opposite angles of the parallelograms here. So these are the opposite angles in a parallelogram are congruent. There's like a million L's in that parallelogram, but we're going to ignore that. So now, number 3, okay, angle EPX and angle JXP are right angles. Okay, this is the definition of perpendicular lines. You form those right angles there. So we have a right angle there, right angle there. Okay, and one of them is shown. And now I'm going to kind of throw together the transitive property with the idea of them being right angles. So it's a little bit of a shortcut here. So angle J, angle JEN, angle A, angle N are right angles. Okay, so this is me kind of trying to cheat my way through an extra line here. All right, so it's really like the definition of right angles being 90 degrees, the definition of congruence being that the angle measurements are equal, and it's the transitive property of all that 90-degree angle stuff. So essentially looking at this picture, because angle P is 90 degrees, the opposite angle in this parallelogram J is 90 degrees. Because this angle at X is 90 degrees, the opposite angle up here at E is 90 degrees. And because JANE is a parallelogram, this angle is congruent with this angle is congruent with that angle. Okay? So this is really a mix of like transitive property. I'll just put transitive property. All right, and that's it. So Jane, Jane, is a rectangle. And this is, again, the definition of rectangle. Okay? Sorry for the long video. Hope you guys are doing well. Take care.